All right, let's jump right into this explainer and unpack the foundational language of engineering, the very rules that keep our modern world from literally falling apart. Whether you're an engineering technology student, a future mechanical engineer, or studying civil engineering, this right here is where it all begins. We're going to build your personal engineer's toolkit today, looking at everything from 3D forces all the way to real-world material behaviors.
Just look at the extreme motion of this roller coaster. Now imagine this running in a massive 3D simulation, cars whipping around a track, experiencing just incredible acceleration. Understanding dynamics and the mechanics of materials is what allows engineers to predict that exact behavior. But it's not just about building it once, right? Think about the real-world maintenance challenges professional engineers face out in the field. They actively use these mechanics to predict metal fatigue and calculate ongoing wear and tear, ensuring that we can enjoy the thrill completely safely year after year.
On the flip side, take a look at the One World Trade Center. It's literally the principles of statics that allow massive skyscrapers like this to withstand incredible wind loads and gravitational forces, all while remaining perfectly, solidly still. And again, for the maintenance engineer, knowing exactly how these static loads are distributed is the key. It tells them exactly where to inspect for microfractures decades after the building opens. So, here's what we're packing into your engineer's toolkit today. We'll quickly cover what mechanics is, its fields of application, the language of units, the SMART methodology, and finally, numerical accuracy. Starting off with Section 1, what is mechanics? The foundation of engineering.
Let's define the macro level of what this field actually encompasses. Mechanics isn't just a bunch of theoretical physics on a whiteboard. It is a highly applied science. It takes the classical physics you already know and applies it to analyze forces, motion, and material deformation. Basically, this is the science that lets engineers accurately predict how structures and systems will behave under different loads to prevent catastrophic failures and ensure maximum efficiency.
Now, these physical reactions basically fall into two main categories of rigid bodies. Statics deals with things at rest or moving at a constant velocity, like analyzing the equilibrium of forces on a giant bridge truss. Dynamics, on the other hand, tackles accelerating bodies, like calculating the force, mass, and acceleration relationship inside a rapidly moving engine piston. Together with the mechanics of deformable materials, these form your core understanding of how the physical world reacts to stress. Okay, let's do a quick knowledge check to cement this idea. Based on those definitions we just covered, which branch is responsible for analyzing the equilibrium of forces on a bridge to ensure it absolutely won't collapse? That's right, it's statics. Moving right along to Section 2, fields of application, where mechanics really comes to life. It is honestly wild how these exact same principles scale across completely different industries. Whether you're a civil engineer designing a massive highway overpass, a mechanical engineer modeling the complex 3D rotation of a wind turbine, an aerospace engineer launching a spacecraft, or even formulating a brand new plastic in material science, mechanics is the universal language you absolutely have to speak. It even extends into bioengineering. Designing a titanium hip replacement requires the exact same understanding of force and stress as designing a steel bridge. And for maintenance professionals in literally any of these fields, this foundational knowledge is what helps them diagnose a failing machine part long before it ever breaks. Time for another quick knowledge check. Which specific engineering discipline focuses on creating completely new materials by analyzing their stress and strain behaviors? If you guessed material science and engineering, you hit the nail on the head. All right, Section 3, the language of units. This is where we set the strict standard for measurement.
In the International System of Units, you probably just call it SI, we deal with kinetic units. The first three are our basic units, and they can be defined pretty arbitrarily. We use the meter for length, the second for time, and the kilogram for mass. Everything you are ever going to calculate will be rooted right in these three fundamental pillars. Now, here's the absolutely crucial point. Force is not an arbitrary basic unit. Force is a derived unit, mathematically formulated to be perfectly compatible with Newton's second law. Force equals mass times acceleration. By multiplying kilograms by meters per second squared, we get our derived unit of force, which we proudly call the Newton. Before we move on, let's test your grasp on the language of units. When you're out there calculating the force on a mechanical part, are you working with a basic unit or a derived one? Yep, you guessed it, it is a derived unit. On to Section 4, the SMART methodology, your step-by-step problem solver. Now we reach arguably the most actionable part of your toolkit.
a brilliantly simple methodology to tackle any complex engineering problem, from a standard textbook exercise to a high-stakes real-world structural failure. The SMART method is your map. Think of it kind of like cooking a really complex meal. Step 1 is strategy. You wouldn't just start throwing random ingredients in a pan, right? You read the recipe, state the problem clearly, and decide what concepts apply. Step 2 is modeling. This is laying out all your ingredients. You draw a free body diagram showing all the forces acting on the isolated body. Step 3 is analysis. This is the actual cooking part, where you apply your fundamental principles and use algebra to solve the equations. Step 4 is reflect. Taste testing. Check for any obvious errors, verify your units match up perfectly, and substitute your answers back into unused equations to ensure they actually work. And finally, step 5 is think. That final think step, it's absolutely essential. Because look, you aren't just a human calculator, you are an engineer. You have to use physical intuition to spot answers that just do not make sense in the real world. If your math tells you a 2-millimeter bolt can hold up an entire suspension bridge, your intuition needs to scream that something went terribly wrong in the analysis step. This is especially vital for maintenance engineers. If a shiny 3D computer model says a rusted pipe is perfectly fine, but your own eyes and experience tell you it's vibrating dangerously, you trust the physical reality and you rerun your numbers. Let's do a quick methodology quiz to lock this in. Which exact step of the SMART process requires you to actually sketch out the isolated structure and the forces acting upon it? For sure, that is step 2, modeling. And finally, section 5, numerical accuracy. The strict rules of precision. For our final tool today, we've got to establish the strict rules of numerical accuracy, simply because your solution is only ever as accurate as your weakest piece of given data. In the real world, engineering data is rarely perfect. As a general rule, the data we get in engineering problems is practically never known with an accuracy greater than 0.2%. So while your fancy calculators and software can spit out answers with 10 decimal places, recording all those extra numbers implies a level of precision that just doesn't exist in the physical materials you're working with. Because of this 0.2% margin of error, we actually have a hard and fast rule for significant figures. If a parameter starts with the number 1, you record it using 4 digits, for example, 15.58 kilograms. But for literally all other numbers, starting with 2 through 9, you record them using exactly 3 digits, like 40.2. This ensures your final answer honestly reflects the actual accuracy of the data you started with. All right, final knowledge check for this explainer. Using the accuracy rule we just covered, if your calculated force comes out to 18.552 newtons, how should you actually record it? Well, since it starts with a 1, you keep 4 digits, making it 18.55 newtons. And there you have it, the whole shebang. You now possess the foundational toolkit. You completely understand the difference between statics and dynamics, you smoothly speak the SI language of units, you know the critical 0.2% accuracy rule, and you have the SMART methodology to confidently guide you through any problem. The principles you've learned here are literally the exact same ones professional engineers use every single day to design, build, and maintain our modern world. So my final question to you is, how will you use mechanics to safely shape the structures of tomorrow? Thanks so much for tuning into this explainer and keep learning.